Can you explain the higher stability of BCl3 as compared to TLCl3? Yes, we can. Why? Watch. BCl3 is predominantly covalent, right? So you have one boron happily joined with 3 Cl atoms. It is beautiful, it is lovely, it is a non-metal chloride, and it is what it is. It's fine. In case of TLCl3, TLCl3 is somewhat ionic. So it involves Tl3 plus ions and 3 chloride ions. Now the problem actually lies with Tl3 plus cation. Why? Thallium has electronic configuration xenon 4f14, 5d10, 6s2, 6p2. It is like this, right? Now out of this you find, sorry, 6p1. Thallium would be 6p1, right? Out of this one electron can be easily lost. If it is lost, I get thallus ions. Very nice. But the moment you want thallium 3 plus would mean that 6s2 electrons also have to be lost. 6s, now s subshell, please understand, s subshell is more closely attached to nucleus as compared to p subshell, number 1, in general. P more than D, D more than F, but S is held most tightly by the nucleus. It is more difficult to lose 6s electrons. Also, on moving down the group, the size of orbital increases. Bigger orbitals means larger volume. If electrons are spread over larger volume, they are more stable. If they are more stable, it is more difficult to lose them. So primarily what you find is, on moving down the group, you find that the reactivity of this electron pair becomes very, very poor. And this is called inert pair effect. And this is called inert pair effect. So what is inert pair effect? Poor reactivity or the lesser tendency of reaction for 6s2 electrons, or in general ns2 electrons, on moving down p block is called inert pair effect. And due to inert pair effect, thallium plus 3 is not very stable. It has a tendency to react and come back to thallium plus 1. And that, my dear, is the reason why thallium plus 3 is not very stable. And boron being at the top is very comfortable with oxidation state of plus 3. So it manages to stay that way. That is the reason.